Welcome to the first part of Math 5, which is about logic. So logic means the study of argument, of deduction, and of truth and falsity. And the first thing we're going to study in logic is called propositional calculus. So propositional calculus is about propositions which are true or false mathematical statements. And what we'll do as we learn about propositional calculus is to develop a formal language for expressing complicated propositions fit together using what are called logical connectives. So that's things like and, or, not, implies. We're going to develop a very careful, concise definition of exactly what constitutes a well-formed formula, and we're going to study how the truth value of a well-formed formula can be assigned and how to compute truth values of well-formed formulas. We're then going to look more deeply at these well-formed formulas from the point of view of logical equivalence, which gives us a way to say when two logical statements may not be exactly the same, but always have the same truth value, which will be very useful in your life as a mathematician when you want to prove things, because often you can reduce a complicated statement to a simpler one, which is logically equivalent, and then prove that simpler one. So that's enough said about what we're going to do. Let's begin with a definition of a proposition. So we have a fairly informal definition here, which says that a proposition is a mathematical statement which is true or false. So the statement has to be true or false in its own right. You can't require any extra further information in order to determine whether it's true or false. So for an example of a proposition, consider 1 is a prime number. I'm not telling you whether this is true or false, but it certainly is either true or false. You don't need any other information to determine that. Equally, the statement 34,043 is the sum of two square numbers. A square number is a number like 1 times 1, or 2 times 2, or 5 times 5, or 1,000,000 times 1,000,000. So this is a proposition because it is either true or false. It might be true or it might be false, but it's certainly one of the two. Next, the square root of 2 is not a rational number. Again, it's either true or it's false. This one's true. And finally, just to make the point that I'm not just thinking about numbers here, we're talking about any mathematical statement. So the unit cube can be cut into 6 tetrahedra. That's a true or false statement. So just to make this clear, let's think of something which is not a proposition. So an example of something which is not a proposition would be something like n squared plus 4 is equal to 7. This thing is not a proposition. And the reason it's not a proposition is because it's not true or false on its own. Right, we're only dealing with things which are true or false in their own right, and you can't decide whether that's true or false until you know what this thing n is. Okay, the other ingredient that we're going to need when we develop the language that we're going to use to express formal logical statements is the idea of a connective. And connectives are things which connect one or more propositions together to make more complex propositions. The connectives we're going to be interested in are and, or, not, and implies. And I'm going to give you an example of how we use those connectives to combine or to make more complicated propositions out of simpler ones. So let's look at the first one I've got here under and. So we have 34,043 is the sum of two squares, and 34,043 is divisible by 17. So you can see here we've got two propositions, so this proposition here and this proposition here, and those two things have been combined together into a new proposition using the connective and, like this. So again, what you've got here is another proposition. It might be true, it might be false, but it is definitely a proposition because for sure it is either true or false. Okay, so the next example connective was or. Here's an example of combining two things using the connective or. Let's just get this right. Okay, so our new statement is 2 is odd or 2 is even. So that is a proposition. It's either true or it's false, and you can see there that we've got two connectives, two propositions rather, which have been connected together using the connective or. So let's look at not now. So the example for not is, it is not true that 34,043 is the sum of two squares. And there you can see we have a proposition 34,043 is the sum of two squares, which has been modified, made more complicated by the connective not. And the final example then is of implies. So we have 34,043 is divisible by 3 implies that 34,043 is odd. And once more, you've got two propositions, so one there and one there. Oops, let's just fix this one. That's better. And they've been connected together using the connective implies. All right, so one last thing. I mean, you might, in your mathematical life, have come across some other connectives. Like there are other connectives which mathematicians use to express their logical ideas. Like they might talk about exclusive or, they might talk about if and only if. Those things are other connectives, and there are even other connectives apart from those. But one of the nice things which we are going to learn about during this course is the fact that these exotic, strange connectives don't actually add anything new. So all of these other connectives can be expressed in terms of the ones I've written on this slide. And in fact, you don't even need all of the ones on this slide.